Hey yo, welcome to this video series named Materials Phenomena in Nuclear Environments. My name's Theo and at the time of this video, I'm a first year PhD student. And this video series is for those of us who want to know what kind of things go on in a nuclear reactor. When you hear things like the neutron damage, oh, it sounds all fancy and stuff. Especially when you talk about let's say sci-fi. It almost sounds like sci-fi, science fiction. But what is it actually about, and what actually happens inside a nuclear reactor? Because nuclear technology does seem to be this kind of really shady, this really mysterious field of knowledge that people don't really know what's going on in there, and it sounds really creepy and scary. Now, I just want to do this video series to kind of demystify what's going on in there. So, of course, a nuclear reactor. Now, you have this little cooling tower looking thingy here. It's a very classical symbol of nuclear power, but that's not where the reactor actually is. The reactor will actually be in a dome-shaped building known as a containment building, and it will look kind of grey and boring on the outside, but that's the building that actually houses this nuclear reactor. And inside this reactor, what's going on? Well, you're gonna have you're gonna have some fuel in there. The basic idea is you have some fuel. Usually it's uranium oxide. And the basic idea is to generate a lot of heat. And why do you want to generate that heat? You want to generate that heat so that you can use it to make steam, to drive a turbine, and of course you get electricity. So in a nuclear reactor, there are at least two things you will need. You'll need the fuel, for one. You'll need enough of it to sustain that chain reaction. And of course, you need some water as well. Alright. But what's going on in there? So basically, the water boils inside this reactor. It generates the steam for the turbine. Or in some other designs, a different approach is used. Now, what do you need inside the reactor? Why isn't it just this fuel and water? Why isn't it just fuel, water, a few pipes, and a turbine? Why can't we just have that? Yeah, so I just draw this little bow thingy here. This little bow thingy here. There's a turbine. Yeah, why can't we just have this kind of a setup where you just have nuclear fuel lying in a pool and some water going in and out? Well, for one thing, as you probably would have known by now, a nuclear reactor is radioactive. When you start burning the fuel, it becomes radioactive and extremely hazardous to human life, and this kind of things can cause cancer. So generally speaking, you want to keep it in some form of containment vessel, okay, to keep all the radioactive material in, and prevent it from polluting the environment and all that. Now, of course, as with all materials, this containment can age or leak or break or fracture or undergo some kind of fatigue, depending on the type of stresses it's undergoing. So it's important to understand the kind of stresses that the material that's surrounding the reactor is undergoing, so that we can understand the failure mechanisms and understand how we can prevent these things from happening. Now, of course, if you want to understand these things, you should have some basic knowledge of material science. For example, what's a BCC structure, a body-centered cubic? What's FCC? In order to understand all what's going to be talked about in this video series. Okay, so yeah, in a nuclear reactor, it's a pretty nasty environment. You have water coming in, making steam to come out, and you have some kind of containment that's trying to hold everything in. And well, are real reactors just, designed like this? You have one metal box, and you have water in, and you have steam coming out. Will this do? Well, not exactly, because when you boil water at atmospheric pressure, it's about 100 degrees C. For those of you who like Fahrenheit system, I think it's 212 Fahrenheit. Yeah, let me check the boiling point of water. It's 212F, yes. Yeah, it's 212F. And if you studied thermodynamics before, you probably know that this is not a very optimum temperature to generate steam at. You probably want steam at a lot higher temperatures, for example, 300 to 325 degrees C, in order to generate a sufficient amount of power for commercial use. So how can we achieve that kind of temperature? For starters, we know that when water is under pressure, it tends to boil at higher temperatures. So under pressure, which is more than 1 atmosphere, water boils at more than 100 degrees C. So the idea is to raise the pressure of this reactor to something like 2200 psia, or about 150 atmospheres of pressure, in order to raise the boiling point to something like this, so that you can get really, really, really hot water. So you probably have a reactor vessel like this, where there's some fuel in there. Okay, so now you have water going in at 2200 psia, and water coming out. Okay. Okay, then you have this turbine thingy here, and you generate steam. Now this is what usually goes on in a light water reactor. Now strictly speaking, there are several different designs. Sometimes, you pump water through the reactor, and the steam generated by the reactor goes into the turbine. That's what is known as a boiling water reactor. Now this pressure for boiling water reactor, sometimes their pressure, I think, is about 1000 psia. But you see, when this happens, you have a lot of the fuel contaminating the water, making the water radioactive, because bits of the fuel actually dissolves in the water and it's radioactive, and it's going all over the turbine. And that's not a very not a very pleasant thing to have a radioactive turbine that you have to maintain every now and then. So what can we do about this problem? So instead of having just one metal tubing around this, or one big metal casing, pressure vessel they call it, around this reactor, what happens is that you have another layer. You have another layer of protection. So this is what is known as cladding. So instead of allowing water to touch these nuclear fuel pellets directly, they'll go past the cladding, which is made of some kind of metal, which is usually zircaloy. And why is that the case? I probably can discuss it later on. But it's made of a zirconium alloy, and this serves to add another barrier of protection to prevent this from contaminating the water. Now, the second thing is that, hey, if we want to mitigate the problems even more, you can even add another layer of protection, so that you have these zircaloy tubes inserted in the reactor. You have this really high pressure, 1000 to 2200 psia. Okay, and what happens is that it goes through a heat exchanger. All right, it goes through a heat exchanger, and then the secondary loop actually generates steam. So this heat exchanger is called a steam generator. This is a steam generator, and over here the water in this loop is so highly pressurized. Actually, it's at the 2200 psi end, or 158 atmosphere end. The pressure is so high that it doesn't actually boil. So this is what is called a pressurized water reactor, or PWR for short. So these are the basic design schematics of classical nuclear reactors that we have nowadays. Of course, if you want to regulate the reaction, you have control rods in here, so that if you push the control rods in, the reaction will slow down. If you push them all the way in, the reactor will shut down. Okay, so this is a very overly simplified way of describing a nuclear reactor. So for BWR, we have high pressure but not that high. For PWR, you have this high pressure loop, and the idea is to get enough high temperature steam so you can get the electricity you need. And of course, you don't want all your radioactive material escaping into the environment. Now, what are the suitable materials that are being used for these that are being used in this vessel, so to speak? Well, you don't have really much of a choice for the fuel, because you do have a few choices, but what is commercially available nowadays is a uranium oxide. But let's say we are stuck with that. What can we do? This tubing is made of zircaloy, as it was said earlier. Why do we need to make it out of zircaloy or zirconium? This is zirconium alloy. It's made out of a lot of this stuff. Well, for any reaction to take place, you need a high enough concentration of the reactants. For the nuclear reaction, the reactants are the neutron and atoms of uranium-235. So you need a high enough concentration of this, and you need a high enough concentration of this in order for the nuclear reaction to continue on in a sustainable kind of a chain reaction. So if the nuclear reaction is self-sustaining, we call it critical, which means that there are enough neutrons going around to replenish the neutrons that are being consumed and the neutrons that are flying out of the reactor, because here will be having lots of neutrons. Some will hit the fuel, some will get absorbed by the water, some will fly out of the vessel. But you need enough of them to stay in the vessel for the reactions to keep continuing. So in a critical reactor, you don't want too many neutrons to be absorbed. So what are the things that actually absorb neutrons? You have things like boron, you have things like cadmium, and these are very good for neutron absorbing materials. And well, actually, if you have enough of them in your reactor, the reaction will stop. And this makes them perfect for control rods, so that if you insert these neutron poisons into the reactor, we will have neutrons being consumed and the reaction will stop. But from day-to-day operations where you do want the reaction to go on, you don't want these neutrons to be absorbed. So we use something that has a low probability of absorbing these neutrons, and the perfect metal for that is zirconium. So that's why we use the alloy of zirconium to help to make up the main component of this zircaloy, which again it contains all these nuclear fuel pellets. Of course, this metal must be strong enough to withstand all that pressure that's going on and the high temperature of like 300 plus degrees C. Any more than that, we will have dangerous things happening, like a meltdown or even the Fukushima disaster, where this zirconium actually reacts with the water here to form hydrogen and then form a hydrogen explosion. So we don't want that happening at all. So these are some of the materials used here. So here we need zirconium. Here we usually have something like boron carbide. And for the reactor pressure vessel, we will have something, the most common choice is usually steel, which is largely made out of iron. Alright, so you can imagine this nuclear reactor is a very nasty environment. The material, this is a very nasty environment. You have a high neutron flux. You have a high temperature of this much, or in case of accidents, we have more. And in a typical pressurized water reactor, you have to have pressures of this much, or 150 atmosphere. And that 150 atmospheres of pressure is a very high pressure. So you have this material that's going through all this, and you have to have no leaking of any sort. Because any leaking of this water, well, that's a radioactive hazard, and if anything gets out, it's a very big public concern. It's not just bad, not just bad PR, but yeah, there are legitimate concerns if too much radioactive material actually escapes. So yeah, we don't want this thing to be leaking. So what are we talking about? Can have small leaks, and we can have large ruptures. And these are the sudden ones. So yeah, so what can cause all these, how can we ensure these things don't happen? So for starters, we will need to understand the phenomena going on inside the reactor. So you may have heard things like stress corrosion cracking, if you've taken materials courses before. You may have heard of things like creep. And you may have heard of things like metal fatigue. Now these are, standard kind of phenomena that happen in materials that are not just happening in a nuclear environment. Yeah, they are not just happening in a nuclear environment, and we have to take note of them so that things like our airplanes, our cars, they don't fail, and the ships that sail on the sea, they don't crack and sink before we expect them to. So you have like other corrosion as well. You have all sorts of these things going on, or even brittle fracture. So knowing that these are the standard kinds of stresses and phenomena that these materials are going to undergo, what can we do to stop all this from happening inside the nuclear environment, especially with environment so harsh? And also, besides the high temperature and pressure, how does this nuclear reaction actually affect all these phenomena? And what's the effect of having this high neutron flux and all this radioactivity going on, what's the primary effect on all these kind of phenomena that's happening. So in order to do that, we want to start with studying some of the things in neutron damage. And in order to start that, we do need some basic materials knowledge, and I'll put some links in the description. There's a very useful playlist I found that explains all this very clearly. And of course, I'll try to narrow down what videos you need to watch before we start each video. So yeah, thanks for watching. So that's all I have for you for this introduction. So just to recap, we know that a nuclear reactor is a pretty harsh environment. This is for nuclear fission anyway. And we know that it needs to withstand very high temperatures and pressure, and we need to prevent it from leaking or breaking very suddenly so that the radioactive material doesn't escape into the environment. And we need to have a good understanding, and to prevent all this, we need to have a good understanding of all these phenomena and how these phenomena is affected by the radiation and the nuclear processes in the reactor, so as to prevent them. So in the next video, we're gonna start on neutron damage. So thanks for watching, and see you next time. Bye bye.